Right, hello. We're just going to do a single video today on something called diodes. Just had to make sure I was going over the right topic. So, well, it's all diodes mixed with a few circuit calculations. Now it does sort of go on from sorry, give me a second. It does sort of go on from the other topic of EMF and internal resistance. So I'm going to assume that you've watched the EMF and internal resistance video even. Sorry about that. So we're going to go ahead and start this. If I go onto the right page. Alright, so I'm just going to do a few calculations. Now, they may not mean anything to you. I'm just going to give you the formula so you know what to use in the exam. So, internal resistance, I'll just put internal R, is equal to EMF, take PD across terminals. Now don't be too worried if you don't know what EMF is or potential differences. Kind of hoping you will go back and watch my other videos on the specific related topics. So I'm going to assume you know what EMF is and what internal resistance is and potential differences. This sort of allows us to create another equation. Well, don't really use that, but cell current is equal to cell EMF. Is that right? Yeah. Over total circuit resistance as put to law. Now EMF is the same as potential difference. You can think of it like that. So this is the same as V equals IR, and as V is equal to E, it is EIR. Hopefully you see where I'm getting this. So potential difference is equal to the EMF or electromotive force. I'm going to assume you know that, so I don't waste my time going over it. No offence, but you know. E equals IR, and you can rearrange that as the same as saying I is equal to V over R. It says exactly the same thing, but you don't write E. You only write electromotive force when you're talking about that. Otherwise, you write down potential difference. I don't think I need to go over that one. Or just the next one that's in the book. Yeah, I don't need to go over that. Oh wait, actually, probably. No, that's more again resistance. Sorry, I'm just picking out equations through the AQA book and making sure I don't pick one that I'm going to go over in another topic. Okay. I've done that. Yeah. So when I say cell EMF, that's also the same as net EMF or total. Just put net EMF underneath as well. You might refer to it as net. Okay, so we're going to what this video was all about. There were just a few calculations that I wouldn't have included in my other videos, so just an extra treat for you. So, what have we got to do? Well, diodes. What are diodes? I'm just going to rub this out actually. This is a load of tish tash tosh, I think. So we'll get rid of all this rubbish. Oh dear, it's been a long day. Right, okay. Ugh. So what is a diode? Well, a diode looks something like this. Say, these two bits at the side, they're your wire coming in and out, and this is your diode, and it's facing that way. So yeah. So is that forward facing diode? Yeah. That's forward facing, just making sure. So what is a forward facing diode? Well, as we know, or hopefully I'm assuming you do, that a diode only allows for current to flow in one given direction. So if it's trying to flow, if it's flowing in this direction, you know that because of the graph for a diode, it looks something like this. So when it starts to increase here, that is approximately something like 0.6 volts. Sorry. And beyond that, it's got no current at all, or infinite resistance. So just put infinite resistance. It's the same thing, just no resistance. I mean, no current, resistance, algebra resistance. Sorry, it's a bit all over the place today. Okay, so we know that when a forward-facing diode is like that, then it must have a potential difference of 0.6 volts, because that's, as we can see on the graph. I mean, there's no labels on it, obviously. I'm just going through it a bit quickly, because I believe some of you may have died during my early videos if you've watched the full 15 minutes. If this is longer, then I'm sorry, but I've tried my best to keep it down. So as we said, anything less than 0.6 volts or the opposite way round, then it has no potential difference between the 2 points. Yeah, so it could be still positive direction, still be a forward direction current in relation to the diode, but if it's less than 0.6 volts as potential difference, then the current can't get through. Basically, it doesn't have enough power potential. Well, it doesn't transfer enough energy to get through, if you can think of it like that. But if you can't, just think if it's less than 0.6 volts, positive or negative, then you can't. It's no current go through it at all. So we've established that. So anything less than 0.6 volts, and it goes the other way. Oh, it just doesn't get through any current at all. Yeah, so hopefully you've understood that. Now, as I said, potential difference for a diode is, it's sort of like a resistor, but you don't have any resistance with it. It just, there's a potential difference of, well, actually you do, but you have a potential difference of 0.6 volts for anything. Yeah. So it's a bit confusing, but there's 0.6 volts if it's facing forwards, or if it's, facing the opposite way to the current, and it has infinite resistance. So hopefully you've gathered that, you've got your head around that. It's a bit tricky, because it can still be positive, but if it's less than 0.6, then you can't have anything through it, technically. Okay, so I think when I was learning about the diode sort of thing, I found this question, I spent probably about half an hour on this question trying to figure out what it was asking. So I'm going to go through it with you and tell you where I found my mistakes. And when I first tried this question, I'm not going to go through it as I did it wrong, otherwise you might get a bit confused, but I'll just tell you what to look out for. So we're given a diagram here. So I'm just going to draw it. So going that way? Yeah. So obviously the larger bar is represented as a positive, and smaller is negative. And it goes positive to negative, the conventional current, and the actual current of electrons goes the other way. Just a bit of information there outside. So we're going to say this battery has an EMF. What's it labelled as? I guess it doesn't really matter, so it could be EMF or potential difference, but I'm just going to leave it as 3 volts, so you can dictate whichever one personally you want to use. So then we've got a resistor. We'll call this Q, and it tells us that's 10 kilo ohms. And we've got a diode, forward facing diode. So as we know, this can go through here. So it's going to have a potential difference of 6 volts, 0.6. So when two resistors, or we can say that's a resistor basically. Just imagine it as a resistor. So is it 0.6 volts? As it's in parallel, the resistor Q is going to have a potential difference of 0.6 volts as well. So we'll just put that on. That is just a common circuit rule you need to know. And then we've got another resistor. Now this is all before I've even looked at the question. I just think, well, when I'm going through, is there anything that jumps out at me? If it doesn't jump out at you, I wouldn't spend a good 5 or 10 minutes in the exam trying to figure out what comes out at you, because you're just going to waste time and it might not be actually needed for the next question. But obviously in this case it is, otherwise I wouldn't be pointing it out. But I'm just saying, as I said then, just anything that pops out at you, just note it down, because it might get you a few extra marks that you wouldn't have done otherwise when you're working out. So this is giving us another resistor here. We're going to call this P, and it's 5 kilo ohms resistance, so half the resistance of that. However, this diode seems to want to go the other way because it's a bit rebellious, like myself. Wearing a United top. Never mind. Okay, so I just put that thing like that, make it a little bit better. So let me just finish going this diagram, and then I'll just go through a few things about it. Apart from it not being straight, and obviously yours will be, we notice that, is it labelled? Yeah, sorry, it's labelled these two X and Y diodes, and obviously P and Q. So we know that the Y diode doesn't have any potential difference because there's no current going through it. So because V equals IR, if there's no current, anything times 0 is going to be 0, so that means the potential difference is going to be 0 as well. So that means Y can't have a potential difference. We're just going to label it as 0 volts anyway, just to, it's just something that would jump out at you by looking at the diodes. Now obviously it's not always going to give you it as parallel. This is just one exam question that is on the book. So is there anything else we can note down that it tells us? No, label it all. Okay, so let's get into the question. So the question says, for the circuit shown, which is obviously this one, I've just drawn it out of the book, calculate the potential difference. So I just put calculate PD. PD is potential difference, but I'm just going to write PD because I'm lazy. PD and current for each resistor and diode. So for each, each resistance. Sorry, my hand went a bit there. For calculate PD. Oh, this should be current as well. I'm just gonna plus current for each resistor and diode. Sorry if it is a bit lackadaisical. I have had the worst night's sleep, but obviously I'm not going to put that on your grades. Hopefully not. Okay, so calculate potential difference for each resistor and diode. So that tells us there is going to be a value. Now, luckily, my genius for anticipating this question, we've already got a few values that we've already put on, and I've explained how we got them. Obviously, if you've not paid attention, you need to go back and check out how we got them, because we're going to be using them for this question. Now, it's all well and good us writing these values down, but how do they help us answer this question? So, two potential differences there. We've got a potential difference there, but we've not got a potential difference at P. And we know this is 0. Okay, just trying to think which way I went about this. Yeah. Okay, let's start with Q. Let's try and work out, because we're saying calculate the potential difference. So I was just trying to think of a way to explain. So it's asking us to calculate the potential difference and current for each resistor and diode. Now, for immediately, potential difference is equal to the current times the resistance of whichever resistor you want to find out. Now, obviously, we're going to need current for that. So, how do we get current from this? I mean, I've wrote absolutely everything, bit of information you've been given in the question in the book. Now, we can't simply add up these two resistances and get us our wait, actually, sorry, one sec. We can. I've just spotted this now. So we've got 0.6 volts there, and we know that in the series the potential differences add up, as we said before, V equals V1 plus V2. And now these are the same, and this isn't in the series, this diode, so we're not going to include that. So we know P is definitely equal to 2.4 volts. If you're wondering how I've got that, it's 3 take away the 0.6 volts from the Q resistor in the series. So that's how we got the 2.4 volts for P. So what does that tell us then? Well, we could work out the current just from Q. That's what I was going to say before. So we've got V, which is 0.6. We've got R, which is, I'm going to keep this simple, 10,000 ohms. You might get confused with kilo, but I'm just going to make sure you don't. So we know V is equal to IR. We want I, so we will rearrange it, divides both sides by R. So V over R, I equals V over R even. That's our equation. We just substitute that in. So we get I is equal to 0.6 volts over 10,000. So let's just put that in our 10,000 ohms. That gets us a current value of 0.6 over 10,000. I'm just going to write it in standard form, so you can convert it into decimals if you wish. 6 times 10 to the 5 minus 5 amps. Now, I'm just going to say it, I will probably have said it in another video if you were watching it, but 1 amp is also referred to as 1 coulomb per second. So you might get asked in a 5 amp circuit how many coulombs pass a given point per second, and you can just say, well, it's 5 coulombs per second because it's 5 amps. Sorry, I just thought, you're wondering what is amp sort of thing. Just to give you a contextual analysis, sort of, really. So that goes to 6 times 10 to the minus 5 amps. So we know that's the current running for the whole of the circuit. It's not going to change. So whatever comes in here has to be out here, and whatever goes here has to be out here. So, I mean, it doesn't lose any current. What it loses is, yeah. So anyway, so we got that current. It doesn't lose that as it goes round the circuit. So it's just the current at Q. And hopefully, if we work it out, yeah, that's going to give us the same current at R, hopefully. At P, is it? Wait. Let me just check. 2 V over R 5. Wait. 2.4 over 5. I don't think it is actually. No. Sorry. The reason why it didn't go to that value is because these are split up. The current goes through both. Both the diode and the resistor. That's why it's asking us to calculate the current in both. So, what do we know? Well, so far we've worked out that's the current at Q. So the current at Q is that. And the current at P, yeah. Is this the right way to go about this question? I'll just do it anyway. So V equals IR, and I'll see I equals V over R. So I equals, for P, 2.4 volts over, was it 5,000, yeah. Ohms. That's it. Right, I know I'm going with this. So, if I said before that at Y we have not got a current flowing through the circuit, then that tells you that all the current is going to be whatever the current at P is. So it's going to be 4.8 times 10 to the minus 4 amps. So that is a current throughout the whole of the circuit. Now we know at Q and X, because it's parallel, the current is split up as it goes through both the resistor Q and the diode X. So we know them too. And we know it doesn't definitely go through Y because it's opposed as the diode's in the reverse direction, so it's infinite resistance. So hopefully you've got that down. I'm just going to give you a minute to pause it and note them notes down if you can see it. If you can't, I'm just going to, you have to rewind it and listen to me again, unfortunately. So, let's get rid of all that info. Dirty, weird. Oh wait, we might have needed that. I'm just going to rub all this out actually. Not a good start. And I'll write down all the currents and stuff that we've worked out so far. So we worked out the current at P was 4.8 times 10 to the minus 4 amps. And I over R. P equals IR. Sorry, just give me a minute. And I equals V over R. Yeah, sorry, I'm just going to have to calculate it again. 10,000. Yeah, 6 times 10 to the minus, thought it was, just had to be short. 6 times 10 to the minus 5 amps. And just put that's at Q and that's at P. Again, we just went through that before, how we got them values. So we know it's split up. So, how can we, I'm going to leave PD, I'm just calculating current so we can work out PD is V equals IR. So we've got these two values here. Now, as I said, I'm just going to do this, create a formula in terms of current for the circuit. So we know the current at P, which is the maximum amount of current because it doesn't go through the reverse diode, plus 0, which is that. The current at 0 at the reverse diode of Y equals Q plus the current at X. That might seem like a weird formula, but it's just one that I created for this question. It's just not really relevant to any other question. So let's substitute in our values. So 4.8 times 10 to the minus 4 plus 0 equal 6 times 10 to the minus 5 amps. I'm just going to put 6. I'm going to leave the. Oh, I just put A. I'll shorten it down to A, so I'm not taking up too much space for my working out. Obviously, you put the units in plus the current at X. So we've got this equation here. So obviously 0 is not going to count for anything. So we can take away 6 times 10 to the minus 5 from 4.8. So 4.8 minus 4.8 times 10 to the minus 4. Just going to put it in brackets so my calculator knows I'm not timesing it by 10, taking away 2, and then timesing that answer by 5 or whatever. So I'm just going to put it in brackets. Take 6 times 10 to the minus 5. And then that should give us X. Basically just rearranging this equation into here, and we're moving the 6 times 10 minus 5, taking it away from both sides. So essentially it looks like we just moved it across and changed the sign. So if we put that in our calculators, I'll just do it now. 4.8 times 10 to the minus 4, so put it as a power, and then do that answer. We'll take that away from 6 times 10 to the minus 5, put that as an answer. And if you've put that in your calculator right, you should get about 4.2 times 10 to the minus 4 amps. Now you may be asking me, well, yeah, it's a very small amp, so have we got another value for that? Because there's going to be many times, not just this one, where we get an answer that's in like minus 10 times 10 to the minus 4, sorry. And it is 0.42 microamps, which is, a microamp is times 10 to the minus 3 of an amp. As it's 10 to the minus 4, we put 0 point in front of it. 42 amps. Hopefully you see how we've converted, and that's microamps. I'm just going to put M amps as microamps. So that gives you the current at Q. So I'm going to rub all this working off here. Hopefully you copied it down. Okay, so let's get rid of all this working here. I'm going to leave the answers on what we've got so far, so we can build on to the next bit. So we know at X we've got 0.4 microamps, 42. At Q we've got 6 times 10 to 5 amps minus, and at P we've got 4.8 times 10 to the minus 4 amps at P. So we've done the currents at the given locations. Now what we need to do is the potential difference for each at the given locations. This is a lot easier, this bit, as we've worked out the main values, and the tricky bit now it's just going back to the start of chapter 4 with working out resistance and potential difference and current. Potential difference, even we've already worked out the current, as I've said. So at Q, V equals IR. Now we worked out that the I is 6 times 10 to the minus 5 amps. So V is equal to that, 6 times 10 to the minus 5. I'm just going to put it in brackets again, times R. Now this is quite a big one, 10,000 ohms, and if you put that in your calculator, just do that now, 6 times 10 to the minus 5. I'm timesing that by 1,000. Oh, 10,000 even. Times 10. Yeah, you should get 0.6 volts. Now, we already knew that because we put 0.6 volts, but I was just proving to you that we've got the right current. Otherwise, if we put in a different value for the current there, then we would have got something else other than 0.6 volts, which is we worked out from the parallel forward-facing diode. Yeah, not good if your teacher has to pause for a second and think, how have I possibly got this wrong? And so it sound like Jeremy Clarkson a bit, which is a worry. Anyway, so with all the new scandals he's been in recently. So that's our value for PD, and we don't need to work it out for this diode as we've given it, and neither of them two, as we've worked it out when we were doing it, when we just first originally looked at the question. Now, I hope that's given you some guidance to these sort of questions. Now, you might get ones that are a bit more challenging than this, but hopefully that's the most you're going to get.